So in the previous video we came up with this formula for working out the length of the flat piece of steel if we want two sides H and W. So just to recall, H was this one and W was this one, and thickness was T, and the key parameter, or the two key parameters to get this to be correct, is this inside radius here and the K factor, which is the fraction of the thickness along which the neutral axis exists down here. So in this video what we're going to do is we're going to try and compute R rather than relying on the rule of thumb formula. So in the previous video I used the formula R is equal to the V width over 6. And one of the comments said, have you measured it? So the answer is yes, I have measured it, and some of them, for some V widths, it's more accurate than for others. So I've done a series of experiments and a series of measurements, and I've computed R and K. So we're going to discuss several ways of doing that in this video. Just the very first thing I wanted to start with this video is just to say that this whole value here, all of this term is called the bend deduction, and you can normally look that up in various tables, which are often in imperial units, which is a bit of a pain. So for metric, I always have to calculate this. It's part of the reason for this video. Anyway, what we're going to do now is we're going to show how we can compute R and K from some measured examples where we've had a flat length that we know length L of the flat, we bend it, we compute, or we measure H and W, so we can compute the value of this bend deduction, and then we can try and solve for R and K, and we'll need to do a whole series of measurements, well, at least 2, and we're actually going to do 8 measurements, and we're going to try and solve for R and K simultaneously in a statistically sound way. So let's get on with it. Right, so as discussed upstairs, we're going to come and do some measurements. So I've got lots of pieces of 1mm steel blank. I've got lots of pieces of 2mm steel blank, all that cut at different lengths from the laser cutter. And we're going to fill out this table that I've got here. So we're going to measure the total length of the flat piece on the vernier, or the height gauge. Then we're going to bend it, and we're going to measure, it doesn't matter where we bend it, we're going to measure the height and the width, and then we're going to measure, using the fancy calipers, micrometer, the thickness of it, and then we're going to do lots of bends with lots of different V's. So if we go over to the press, if I can master this camera, so as discussed we've got 16, 22, 35 and 50, and we're going to do a test bend in 2mm steel and 1mm steel on each V. So let me just illustrate the measurement of it. So the first thing to do is to measure the height, or the full length, before we bend this piece. So we'll do that. We've got 160.11. Then what we'll do, I'll just write it on there. Then we'll measure the thickness. So I normally find that the 1mm is always a little bit thinner than the nominal 2mm dimension, so we'll just measure it. I'm sure there are better ways of doing it, but this is good enough for these purposes. I don't know that we can see that, but that is 0.891 millimeters thick. So we're going to do a bend on this part, and for the purposes of this example we'll do it on the 50 millimeter V. So we're going to bend the piece we've just measured. It doesn't matter where we bend it, because we're just going to add the two numbers together. So all we're interested in is how much the material stretches or compresses around the bend. So get that on there, it's square, and let's bend. Right, so I'm going to measure that. That's in the 50 mm V, so the radius is quite big. I'm going to measure the height or H and W of this part on the vernier gauge. Okay. Well, first of all, we'll check if the bend was square. Seems reasonably so. Right, that's our first number, 77.39. And then the other dimension is 86.98. So that's our first entry in the table. So we've just got to do that again with 2 millimeters or nominal 2 millimeter thickness on this 50 mm V, and then for each thickness that I'm going to test, just for now just 1 and 2 on the other 3 V sizes as well. So magically we shall bend some metal and the table shall be full. So I bent lots of bits of metal. I have to start the table again because I messed up writing a few numbers in it, but this is all the experimental observations that we've got. So we're going to go and type these up, and then we'll do some calculations to work out what the bend radii are for each V, and hopefully we'll be able to calculate the K factor as well. Just one point I wanted to illustrate, and the reason for this activity is, so this is a 2.5 millimeter radius gauge, and the V width over 6 formula tells us that the inside radius here should be 2.67, but obviously one doesn't have a continuum of these radius gauges, so 2.5 is the nearest I've got. Is it nearest I've got? Yeah, I think it is. I think the next one's 3. So if I try and do this on camera and register it, you can see that it's actually quite a good fit for the radius, so we're not far off. But measuring the difference between 0.5 and 0.67 might be a bit of a tall order with this kind of technique. We can measure the outside radius as well. Again, the nearest one I've got is 4.5, and we should be able to see, if that focuses, that is quite a good fit there. So I've typed up the table from the workshop. These are all the measurements I did. So for V width 16, I had material thickness nominal 2 millimeter, nominal 1 millimeter. I measured the length. I then bent it at some arbitrary point. I measured the 2 flanges, and then using that, if you subtract these 2 from L, you can get the bend deduction, which is this bit here. So we can then use that number to try and compute the values of R and K. Now I'm going to do it just by rearranging the equation first of all, and then I'm going to set up a least squares solution for this. And if you're impatient and just want to know the answer is that the V width over 6 formula seems to hold for 16 and 50, and is much less accurate for the 2 sizes in the middle. So how do we compute the radius from these measurements? So we'll just go back to the formula. That's what we've already said. And then we can just rewrite this bit as the bend deduction, and then we can rearrange it all to compute R like that. And this bit, of course, is just the bend deduction column. So we can take our measurement data and we can compute some more columns in our spreadsheet. So I'll just zoom in on this. So up to here was the same as the spreadsheet before. This was the radius using the V width over 6 rule. This is the K factor, which we just looked up for now. This is the deduction that we would have computed if we'd used this value of K and this value of R. And this is the error between our computed deduction and the measured deduction that I've just made on the press. And you can see that the error, in some cases, is quite small, 0.1, 0.02, and again up here, but in the middle, the error gets quite big. And you can see here that the actual radius, if you compare these two, so that's okay for the V width 16, but for the V width 22, we're 5.1, 5.3, and over here it's 3.6, so we're quite a long way out there. And similarly for 35, 7, 6.97 versus 5.8, so again that's quite a long way out, but we seem to get back into kilter with it here. So we've just shown that, at least for my setup, my tools and everything that I'm doing, the V width over 6 isn't a great approximation for the middle two V sizes. Now, it's quite hard to measure R down to this accuracy. So I'm now going to explain how we're going to compute R and K simultaneously for all of the different V widths using the least squares technique. So there's a very common problem formulation in signal processing and machine learning and all sorts of other disciplines where you can set up a matrix A. There is a vector of unknown variables x, and you equate this to some measurement vector b. Now, if everything's perfect and the model is perfect, all this holds, but when you do measurements in the real world, there's always some error here. But if your model is linear, then you can choose to solve the problem. Minimize ax minus b over the x variable, and the system will choose values of x such that this fits your observations and your scaling matrix A. And it turns out that in our particular problem we can fit the bend deduction formula and our measurement observations into this formulation, and then we can use a standard solution to this. We'll come on to that in a minute, but basically we can say that our solution x star is equal to the pseudo inverse of A times B, and this can be computed in your favourite maths package and is based on the singular value decomposition of A. There are plenty of other ways of computing this, but this is a nice numerically stable way. So what I'm going to do now is I'm going to show how we formulate this particular problem, write the elements of A and B and X, and then I'm going to put it into Octave, and I'm going to come up with a solution which will give us both K and R simultaneously for all values of R and K, because we have an overdetermined system. Because so we've only got 4 radii to determine and 1 K factor, so that's 5 variables, and we've got 8 equations. And if we wanted to go to town, we could do many more observations at different thicknesses, as long as the equations are nominally linearly independent. Right, so let's crack on with this and formulate it. So let's just write the formula out yet again. We could have done it for the general angle case, but it seems a bit error prone to carry around all those tan theta over 2s everywhere. Right, so that's like that, and then we can write L minus H minus W is this. And we're going to call this the bend deduction, and we're going to write that as D. And in our measurements in the table, we have 8 measurements of D. So we've got D0, D1, D2, all the way up to D7. And we've got each one of these corresponds to a different thickness and potentially a different radius. Now we'll notice from this that the unknown variables R and K enter linearly. So if we just pick, let's just write down for the first one. So we'll say D0, which was for the V width 16. So we can write D0 is equal to 2, the radius for the 16 millimeter V width, plus T, and our thickness for entry 0, so we're going to call that T0, which just happened to be 2 millimeters, plus pi over 2 times R, 16 again, plus K, which we're going to let this system solve for as T0. So what we can do is we can write this in matrix form, and we can sweep D, T and R over the matrix. So let's write this down. So we can write K, because we're going to assume that K is constant for all of the bends that we're doing, because it's all steel, it's all hopefully from the same batch, although different thicknesses. And then we're going to write R16, then we've got the radius for the 22V, the 35V and the 50V, and for convenience we're going to write a 1 here, which I'll explain in a minute. There's a word for that, I can't remember what it is. And then this is equal to our measurements. So we'll start off with D0 at the top. So we can write this whole expression out in this matrix here. So we know that we're going to have a pi over 2 times T0 multiplied by K. So pi over 2 times T0 for this first element, and then we're going to have, so R16 is multiplied by pi over 2 minus 2, so that's the second entry in the matrix. And then none of the other radii feature in this first expression, so there's no R22, there's no R35, and there's no R50. But we do have a minus 2T0 written there. So if we were to multiply that out, we'd get D0, we'd get pi over 2 times T0 is K, plus R16 times pi over 2 minus 2, minus 2T0. And we can do the same for the next measurement. So the next measurement, I'll just write out what that would be. So that's D1 is minus 2. Again, that was a 16 millimeter V, plus, by this time it's T1 because it's thickness 1, which in our case is a nominal 1 millimeter, which in the spreadsheet of data ended up as 0.88. Plus D1 plus pi over 2, again R16 plus K, K is the same, T1 again. So we can write that out in this matrix again, which is the same thing, pi over 2 times T1. This column will be constant for each radii, 0, 0, 0 each radius, and again, this is minus 2t1. So we've got our two observations and we're using them here. And then for the next variable, we've got the same thing in the first column, 2, but we're not featuring R16 this time, but we will be featuring R22, and then we've got 2 more zeros, and then we've got minus 2t2 and d2, and so on, and we can populate this whole matrix, which I'm not going to do by hand, but we will have a look at on the computer. So I formulated the matrix in the spreadsheet, and then I transferred it to Octave. So I've got the matrix, and you can see the sort of structure of it, and the multipliers of the radius are constant, and then these depend on the material thickness. And then this last term also depends on the material's thickness. And then we can solve it with using the pseudo-inverse technique. And we get some solutions, and the very interesting thing about this is that x comes out at 0.438 and the textbook, sorry, not x, k comes out at 0.438 and the textbook value was 0.44, so pretty close. And then we get these radii out, and these differ slightly from the calculations that I did without using the squared solution. So if we go to the other spreadsheet, so the values that we get are 2.43 and 2.63 when we did it individually, and we've got sort of an average value of 2.47 when computed. That's for the v width of 16. Sorry, v width of 16. So this is kind of an averaging across them, and if we did lots of measurements, we would probably get a much more accurate result than I've got here, but this is pretty good. So just to reiterate, the formula for v width over 6 doesn't hold for the numbers in the middle, 22 and 35, but does seem to be fairly accurate for the 16 and 50. And it's all quite reasonable because the number that should have come out as 1 came out as 0.9995, and the k-factor agreed with the textbook. So I just wanted to conclude with my experimentally determined inside radii corresponding to each v width for the benefit of anyone watching and my future self next time I need to do this. So there we are, there are the numbers. I'd be interested to know if anybody else goes through this process and comes up with similar numbers. Comments below.